So, hello and welcome to this Ask a String Theorist session. My name is Ana Luisa, and I am one of the outreach coordinator at ICTP-SAIFR, sponsored by Serra Pileira. Today's session is one of the outreach activities from String 2021 conference that this year is organized by SAIFR. But before we start, I'd like to talk a little bit about our center and what we do. SAIFR is the South American Institute for Fundamental Research. We are institute partnership from ICTP. Maybe somebody has his. I'm sorry. SAIFR is the South American Institute for Fundamental Research, an institute partner from ICTP in Trieste. We are in São Paulo, South America, but we have linked with many other institutes from all over the world. The center started in 2012, and we are growing quickly, as you can see by these numbers. We received more than 7,000 visitors during the last years, among students, postdocs, and professors. In addition to all the research and training activities, we also have outreach programs. We have a special program in a museum in which physicists and artists are bring together to discuss a topic in common. We also have informal public lectures in a bar, so you can have a beer, meet your friends, and talk about physics. For high school students, we have a program that professors taught mini courses to students to bring university closer to them. We also organize visits to public schools, so students can ask questions about physics and science, careers in science. For high school teachers, we have a program in partnership with Perimeter Institute. We have translated all the resources from Perimeter into Portuguese, and now we train the teachers to use these materials into their classrooms. As we receive a grant by American Physical Society, we are able to translate this material into Spanish as well. So now we have this program in Spanish. And through these workshops, we are organized a network from high school teachers all over Latin America. As with the pandemic, all our activities are now online, including the ongoing String 2021 conference and a public lecture series on our YouTube channel. Yesterday, we had the pleasure to receive Professor Jim Gates from one of these lectures. So if you missed it for any reason, you can still watch it. They are online on our YouTube in Portuguese and in English. So if you got curious about what we do and want to know more about our outreach program, I invite you to follow us on social media. They are on the screen, but also on the video descriptions. So today, you are going to be able to ask a panel of distinguished physicists from String Conference all the questions that you have always wanted to ask. This session will be moderated by Professor David Gross, who received the Nobel Prize in 2004 for the discovery of asymptotic freedom in subnuclear interactions. Professor Gross has been involved with SAIFR since its creation and received an honorary doctorate degree from our university in 2006. So thank you all for joining us today, and thank you, Professor Gross, the panel of journalists, and all the string theorists that are participating in it. I hope you all enjoy it.
So, welcome. Welcome to everybody. Am I on?
Yes, it's you, Dave. Go ahead.
Okay. Welcome, everybody. It's nice to see you all. We have a very unusual occasion today. We've just completed the first week of a 2-week, very exciting Strings conference organized brilliantly by our Brazilian colleagues and their friends in this difficult time. And today we have gathered almost all of the speakers at this conference, a remarkable collection of string theorists from around the world. And this is your opportunity to ask a string theorist whatever you want and to hear from some of the most brilliant physicists in the world. If you want to ask a question, you should enter it on the Q&A on YouTube. Please make the question short and clear, and attach your name as well. Now, we're not going to be able to get to all of the questions, but hopefully we can get to many of them. I also, would like to introduce, before we begin, our distinguished panel of journalists. And they are, in alphabetical order, Graham Farmello, who is a former particle physicist, but now a distinguished writer, the author of a wonderful biography of Paul Dirac. And more recently, he's written a book entitled The Universe Speaks in Numbers, which is about the interplay between fundamental physics and pure mathematics, which is quite relevant to string theory indeed. Our second journalist is Jandira Oliveira, who got her PhD in physics at the Brazilian Center for Research, and she coordinates the scientific activities of the Institute. Our third journalist is also from Brazil, Marcos Pivetta, who is the science editor at Pesquisa Fapest, which is a Brazilian science news monthly magazine. And finally, Henry Reich is the creator of stick figure science channels, Minute Physics and Minute Earth, which are quite marvelous, and I urge you to look them up on YouTube. He also studied physics at the Perimeter Institute for Theoretical Physics. So these journalists have helped us formulate, choose these questions, and they will be intervening at various points in our discussion. Now, we're going to start with a question that we all ask, and I'm sure many of you ask as well. And for this question, we have already a bunch of people who have agreed to answer this extremely difficult question, namely, what is string theory after all? And again, I'm going to go in alphabetical order, starting with Miriam Svetic, who is at the University of Pennsylvania. Miriam.
Well, thank you, David. I have somewhat standard response to that, and I would consider string theory as the prime candidate. Actually, according to David, the only game in town for quantum unification of gravity with other forces of nature.
Okay. Second is Juan Maldacena, who is an Argentinian physicist, but now working at the Institute for Advanced Study in Princeton.
String theory is a theory trying to describe the quantum mechanics of space-time. So trying to explain how space-time behaves at very short distances and also at very large scales, because the beginning of the universe joins short distances with large scales.
Okay. So we now turn to Shiraz Minwala, who is an Indian string theorist working at the Tata Institute in Mumbai. Shiraz. You're mute. Yes. Unmute.
Sorry. I feel that string theory is the most powerful, all-encompassing and far-reaching framework for consistent mathematical thought in physically relevant contexts, yet stumbled upon by human beings.
Luckily. Okay, now we'll go halfway across the world to Hiroshi Uguri, who is a Japanese string theorist working at Caltech and in Tokyo. Sure.
Hi, so I'm from the antipodal point from Brazil. So string theory is a theoretical framework to unify general relativity and quantum mechanics, which in certain situations are well described using extended objects, such as strings, as fundamental constituent. There are cases when ordinary approach fails, and in those cases, having string as extended object as fundamental constituent helps.
That's a great description in one sentence with many commas. We now turn back to India to a distinguished string theorist who is now working at the International Center for Theoretical Sciences, Ashok Sen. Ashok.
In my old-fashioned view, string theory is a proposal for describing the laws of nature in which the fundamental constituents are one-dimensional objects called strings instead of point particles.
Great. And now is the turn of Eva Silverstein, who is a string theorist at Stanford University.
Thanks, David. I would say string theory is a work in progress aimed at formulating space-time physics from first principles, with one of its major goals being to understand the observed accelerated expansion of the universe.
Wow.
Okay. And next is one of the organizers of this meeting, a Brazilian physicist, Pedro Vieira, who works at this institute, Sophia, ICTP. Pedro.
So I would say string theory is a theory of quantum gravity that describes big objects, which, however, can see as emergent from a theory of point particles with only quantum mechanics.
Okay. And finally, and quite appropriately last, Edward Witten, a string theorist who works at the Institute for Advanced Study in Princeton.
String theory is the framework in which physicists have had some success to understand what there might be at a deeper level than the really established framework of physics that we already have.
Right. Very close to the way I think about string theory. It's an extension of our extraordinarily successful framework of quantum field theory, which enables us to hopefully understand the dynamics of space-time, as well as unify the forces of nature. So these are answers to, you heard, there's not one answer to what is string theory. It's a question which we're still questioning. So we're going to turn now to the questions from the audience. And these have essentially been chosen from the many questions that are beginning to appear. This one was chosen by Henry Reich, but it was asked by Lelrond, who asks, as far as I understand, string theory is enmeshed in a scientific controversy. What are the most common misconceptions on both sides of the controversy about string theory? That's a difficult question. So, in other words, there are people who criticize string theory, perhaps being unscientific. There are people who believe that string theory is the only answer. Are there misconceptions on both of these sides? Anyone up to answering these questions? Hiroshi.
Yes. So I'm not quite sure which controversy that the questioner is asking about, because there are certainly, this is an active area, work in progress. So there are lots of interesting intellectual debate about the field. And there are certainly important questions. To me, the most important question is the string theory is yet to be verified experimentally and by observations. And string theory is a part of science, and science makes progress by proposing assumptions, building theory, and having its prediction tested by experiment. And since string theory has not been verified that way, so there are lots of rooms to question some of the validity of the claims. And I think that some of the controversy has to do with the fact that we are working on a very, very difficult program. And therefore, it takes a long time for us to be able to produce experimentally verifiable predictions. And some people have gotten impatient about it, I'm afraid. But I should point out, for example, the atomic hypothesis took 3,000 years to be verified.
Jerome Gauntlet, you would like to give a response.
Yeah, I'd just like to, I should introduce myself. I'm an Australian physicist, but working at Imperial College in London. I think there's many approaches to quantum gravity. And one of the interesting things of the evolution of string theory is that many aspects about quantum gravity, which were thought not to be string theory, actually have become incorporated into this richer and deeper structure that we are now studying at this conference. It's also interesting to point out that there's many string theorists who are very open-minded about lots of different approaches to quantum gravity. I firmly put myself in this category because my wife works in quantum gravity, but not on string theory. And we happily cohabitate, we happily talk about physics, and we share the enthusiasm of the desire to find the deeper structures underlying what quantum gravity is. So it's a work in progress, there's different routes there. And I think my own approach and take is that the more open-minded we are, the more likely we are to succeed in that final destination.
Can I ask a follow-up question there, which is just that you mentioned that various things that have been discovered or proposed after string theory have kind of gotten wrapped into string theory. How much of that is discovering actually that these things are mathematically equivalent to string theory, and how much of that is string theory expanding what it labels?
That's a good question too. I can speak from my own personal experience. I began my PhD in Cambridge in 1987, and I was working with Paul Townsend on D=11 supergravity and membranes. And it's hard to communicate a little bit to young people in the field today. But at that time, those subjects were considered to be fundamentally heretical to string theory. They were considered to be alternative approaches with almost no overlap. And the string theory community at that time decided that they were distinct subjects. However, in the 1990s, a period of great activity and understanding of string theory uncovered that those two things I mentioned, D=11 supergravity, and these extended objects, membranes with two extended dimensions rather than one, were actually components of this bigger mathematical structure. Now, the end of that process is not over because, as the very first question indicated, what is string theory? We still don't know what the answer to that is, but we've learned that certain other mathematical structures with interesting physical properties have been incorporated in this deeper and more fundamental structure.
So there's obviously controversy about validity or alternatives to string theory. Maybe I'll turn to a question that from Abu Omayar, who Graham Formello thought was a great question. What are some of the problems that string theory has solved so that we might have confidence that we're in the right direction in the pursuit of quantum gravity? Juan, would you like to address that? Unmute yourself.
Yeah. So the first success of string theory was to formulate the perturbative theory of quantum gravity. So a theory where you can calculate corrections to various processes, like scattering of gravitons in flat space. So very simple, idealized processes, but for which you get at least a reasonable approximation to an answer. Another area is to find relationships between string theory and more ordinary theories of particle physics, such as gauge theories. And in this relationship also establishes a connection between this more formal developments in string theory and the actual strings we see in experiments. So actually, something people might not know is that strings have been already detected in experiments. And these are the strings of quantum chromodynamics, which we now explain in terms of chains of gluons, or the particles of a strong force. But these are relativistic strings, somewhat similar, and in fact, you could say almost the same. I could go on a limb and say that they are the same as the strings that we normally deal with, but that they live in a very special curved space and so on. And so these connections, this is just an example, but there are also other similar connections between particle physics and string theory. String theory allows you to discover dualities or relationships between different theories of particle physics. And so I think these are some of the results in string theory, and some of the things that we interpret as telling us that we are somehow in the right direction. There are also many insights of string theory into mathematics. I think that's just evidence, not necessarily of the correctness of string theory, but of the rich mathematical consistency of string theory.
On the other hand, as Rafael Porras asks, or comments, since the discovery of string theory in the 1980s, it has never made a prediction that experimenters have verified. Does this worry you? And can you identify any prediction of modern string theory that stands a reasonable chance of being checked experimentally in the next 20 years? Eva.
Thanks, David. I'd like to address this question, and also it's related to some of the earlier ones. So before we get to the real experiment, let me just articulate something that's implicit in what others have said, which is that thought experiments play a big role in physics historically. And there are thought experiments involving black hole evaporation that have been greatly informed by string theory results. When it comes to the real observations or experiments, it's a tough thing because of the separation of scales. For many purposes, our experiments simply don't get to energy scales that access the fundamental physics of the theory. But there is an exception to this, which is in early universe physics, where there is some sensitivity to quantum gravity effects. And it's there that we make predictions that are not universal from string theory, but which are what we call model-dependent predictions. We model the physics of the early universe using the correct framework, which is a theory of quantum gravity. And then when we can use real observations to discriminate among those possibilities and test some of them. And those tests are ongoing, involving things like primordial gravitational waves and other aspects of the distribution of matter that we see in the universe.
Okay, no one else wants to take on that challenge? Gabriele.
Gabriele Veneziano, Italian, and living in Geneva and Paris. So now I wanted just to say something about the way to test string theory. What I would like to say is that string theory offhand does make predictions, but unfortunately they're usually wrong, and we have to find ways to avoid those predictions. Let me make an example. In string theory, there is gravity automatically, but there are typically other long-range forces that we don't observe in nature. They are due to some massless particles in the theory. And we have difficulties still trying to get rid of all these extra interactions, which we know experimentally are not there. So it is not that string theory cannot be falsified. I mean, like the old string theory that Juan Maldacena was talking about, which was falsified, the old theory of strong interactions. This theory as well can be falsified if one can work hard enough. Or maybe we can solve all these problems and show that the theory stands on its feet. Okay, that's all.
Graham, you wanted to follow up on the question?
Yeah, it's just a general comment that might be helpful to some of our listeners. I was speaking from Cambridge, where about a kilometre from where I'm sitting, Lord Rutherford used to say, "I'm a simple soul, please explain quantum theory," to Paul Dirac. Now, I think many people would appreciate understanding why string theorists are so confident about the framework that they're investing their careers in many senses, right? With so little experimental feedback, something that Rutherford and most people in other branches of science would take as absolutely essential to what they're doing. But theoreticians are take their encouragement from mathematics, the clues there that Juan spoke about, and other things that you may wish to tell us about. But how is it, from where do you derive your confidence that leads you to stick with that framework?
Okay. There are many answers to this, indeed. Some of them Juan referred to. Edward, would you like to try to answer that?
I'll make a few remarks. So, of course, the first thing that made physicists take string theory seriously in the context we're discussing today is that in conventional quantum field theory, the framework where we understand atoms and subatomic particles, it seems to be impossible to include gravity, while string theory forces gravity upon us. Now, that's not usually regarded as a prediction of string theory because the gravity was known long before any string theorist was born. But it is a striking fact that string theorist forces us to have gravity and quantum mechanics, and otherwise, as far as we know, that's not possible. There's something which is a little harder to convey, I think, to a wide audience, which is that the mathematical structure is incredibly tight. It's amazing how it fits together consistently and actually works. And in fitting together so consistently, it shed a lot of light on both other theories of physics and, as Juan mentioned, even various areas of mathematics. So my view is that either string theory is on the right track or there's an incredible cosmic conspiracy. Of course, can't necessarily expect everybody to share that view. I can only explain my own view.
Right. I'd like to just strengthen that in the sense that we have an extraordinarily powerful and successful framework for understanding the ordinary forces of nature and the constituents of matter. It's called the standard theory, the standard model. And the remarkable thing about string theory is how well it fits into that framework and extends it and often gives a dual or complementary description of physical phenomena which have been extraordinarily well tested. So this is, to some extent, string theory is not revolutionary in the sense of fitting and complementing and extending our very successful framework, which has extraordinary experimental confirmation. Okay.
David, can I ask one follow-up question there? Which is just that, that like Edward mentioned, that string theory is an incredibly tightly kind of fitting theory and constrained both within itself and also in connection with the standard model. And given that, how does that give you confidence that if it's not currently working, how does that give people confidence to keep going? I understand that's what makes it hard, is that it's very tightly constrained and then it's hard to tweak it to make it work. But why does that make you think that you should try tweaking it rather than throwing it out with the bathwater?
One answer to that is there's no other game in town. If there was, and maybe we could open that to this panel as well. Does anyone think there are other games in town? It is not easy to do fundamental physics and to construct new or enlarged frameworks that have a chance of success. And the other answer is, of course, we have no choice. The fact that we can't directly test predictions of string theory is partly because there's inherent in the structure of nature, we have discovered an enormous scale between the regime which we can probe directly today and the fundamental scale of string theory, which is removed by many, many orders of magnitude. That's a fact of nature. We have to live with it, and we really have no choice. But there are other people who would like to. Samir, chime in. Samir Mathur.
Hi, I'm Samir Mathur at Columbus, Ohio, in the US. I just wanted to note that there's a remarkable fact which was observed through string theory, that the entropy of black holes works out perfectly. So one can actually make arguments from thermodynamics, which are very robust, that a black hole should have so many configurations inside it for so much given mass. And if a theory can actually compute the number of configurations and gets a different number, the theory just has to fall because it is in conflict with thermodynamics. But string theory managed to compute that number and get it exactly on the dot. And I think that really told us that the degrees of freedom we have in string theory, these bizarre things like strings, brains, all these things we use, they must be there and exactly the way that we use them, with not even a factor of 2 wrong anywhere, to match up with a thermodynamics prediction. So it is as important as saying we knew the laws of gases, but when we got the atomic structure of gases correct, we could get, for example, their specific heats correct down to the last factor of 2. Diatomic gases have one specific heat, triatomic gases have a different one. It's at that level that we actually got the match. And I think that is just fantastic. So I think it tells us that whenever we finally understand gravity, it somehow must have this structure that we have uncovered from string theory, at least when we go to high enough energies. At low energies, it's very unclear, but high enough energies, it should have the features of string theory.
Right. The success in counting the number of microstates of a black hole in string theory is a great prediction that has been of unfortunately, just a thought experiment, but one that has been verified by calculation. And there are others. Ashok, you wanted to make a comment.
Yeah, I just wanted to make one clarification to Henry's point that it's not that we are tweaking string theory. In fact, if we could tweak string theory, we probably would have gotten the standard model long ago. Okay, I mean, the main problem in string theory is that you cannot tweak the rules. Okay? And that's why it's so difficult. When the rules are given to you and you have to play the rule, go by the rules. So it's impossible to tweak string theory.
Of course, we don't know all the rules yet. Miriam.
Yes, I just want to follow up on the driving idea of unification of forces and the tight mathematical structure of string theory. Actually, it's a non-trivial, in my view, answer that we can actually do get consistent string theories that, of course, include quantum gravity, but they unify quantum gravity with particle physics. And by now, our techniques have been developed, maybe too developed, that we are obtaining this structure of standard model with advanced geometric techniques. And in my view, this is quite interesting and amazing property of string theory that no other theory could actually achieve. Thank you.
Okay, I think we're going to, there's been a lot of discussion of black holes and the success of string theory. So there's a question from Fernando Faria. Does string theory explain the singularity in black holes? This is, as you...
I would take that one. The answer is short, no. So we haven't understood string theory well enough to explain that. And this is certainly one major shortcoming of our theories and a major thing that we'd like to understand. And we like to understand not only because there are black hole singularities, but also because it's similar to a big crunch singularity, similar to cosmological singularities. So if we could do that, it would be really wonderful. And that's one of the main reasons we're studying black holes, to be able to understand the singularity and eventually to understand the beginning of the Big Bang, hopefully sometime very soon.
Right, so that's a, on the other hand, there have been claims recently that string theory allows us to solve the black hole information paradox. So Lorenzo asks Pedro, as a fellow Brazilian, how is the black hole information paradox treated in string theory? What is the paradox anyway, and how does information get out of the black hole? Pedro, I'm not sure you want to take this, but are there other people?
I can take it and describe the very, very basics of it, but then I'll leave it to the specialists who really work on black holes. So there are two things that black holes do as thought experiments that are very convenient and very inspiring for us as string theorists. So one of them is indeed this black hole information paradox, which is the idea that if you throw stuff into the black hole, the stuff falls into the black holes. Black holes are this object that nothing escapes. And because they fall into the black hole, we cannot see them anymore. And therefore, the information is lost. Now, why is this a problem? The problem is that if the black hole could somehow disappear, and that's another question, how could the black hole disappear? But it could. Then that information, it looks like it will disappear forever. It was there, it went into the black hole, and now it's no more. And physics says that this should not happen, that information should be preserved. We should be able to go back and see the information. And so this is a good thought experiment, because then we have to understand, how do we evade this? Is this really a puzzle? Is it not? How do we solve it? And the other question, that the other problem that is the other inspiring features of black holes that is very much related to string theory, and maybe that's related to the question and why it would connect to what I was saying in my response about what is string theory, is that thinking about black holes led to a surprising idea, which was that the information inside the black hole, the amount of information, looks to be proportional not to the size of the black hole, but to the area of the black hole. And that could be a detail, but then the more people thought about it, the more they seemed to understand that that was a fundamental idea. And that's very counterintuitive as well. Normally, if you have a room that is twice as big in volume, you can put twice as much information inside. Not with black holes. If the black hole has twice as much area, you can put twice as much information inside. And again, people are taking this idea seriously, and a lot of the development in string theory comes from taking these general thought experiments and pushing them further and further and seeing where they lead us.
Samir, you want to tell us that there is no singularity, correct?
Yeah, thanks. So let me just describe some studies we have been doing with black holes in string theory for many years now. And we seem to find the following. When you try to make a black hole in string theory, you of course have to use the strings and brains that you have in the theory to make the black hole. And normally you would have thought all this mass would go to the center like predicted by classical physics and leave you with an empty space and a horizon. But we find every time we try to make a black hole, that is not what happens. So this bound state of strings and branes, it just fluffs up and becomes a big object equal to the radius of the black hole. So you get something more like a planet or a star. That's a remarkable feature of string theory, that normally you thought that all effects of string theory or quantum gravity would only be at like a Planck scale or very short distances near the singularity. But we are finding there is no singularity. We could never get any configuration with a singularity. The whole thing always fluffs up into this ball whose radius is the size of the horizon of the black hole. So if that is the case, then for all the things you could do with string theory, then in fact, all the puzzles with black holes go away. You never actually have this troublesome horizon or Hawking's puzzle. You just have something which is more like a string star. And so all the cases we have tried so far have worked out like this. We call this the fuzzball paradigm because people started calling these fluffy objects fuzzballs. And if it is indeed true that all black hole states are like that, then we have indeed learned something very remarkable from string theory. So not everybody is certain that all the states would be like that, but assuming they are like the states that people have found so far, this would be an answer both to the singularity question and also to all the paradoxes like the information paradox.
Okay, I'm going to turn now to some slightly more basic questions about string theory from some of the audience for which all this is probably rather new. A lot of them have to do with space and time. For example, from Master Mio's channel, the question is, I heard we need to find more dimensions in order for string theory to work. Apart from X, Y, and Z and time, what other dimensions might there be or have to be? Who would like to explain why we're drawn to think about higher dimensions in string theory that we don't see? Hiroshi.
Thank you. So, so one of the very, very interesting features of string theory, which is not there in other theories such as Einstein's general relativity or Maxwell's theory of electromagnetism, is that string theory requires that dimension of space and time to be certain values. So for example, electromagnetism can be defined in any dimensions, and the general relativity can be discussed in any dimensions, but string theory has to be defined only in certain dimensions. That dimension turned out to be not 3+1 in our universe, but fortunately it was bigger. So there was a way to deal with this if we understand how to deal with this extra dimension. And when I was a graduate, when I was first-year graduate student, remarkable discovery was made to deal with this. And at the same time, these extra dimensions give rise to very detailed, beautiful structure of standard model of particle physics. And some of the authors of the paper, such as Edward Whitten, is here. I was very fascinated by this when I was a first-year graduate student, and that made me into this field.
Edward, do you want to comment?
I'll just make a general comment. So there are many, many elementary particles known. By traditional definition of elementary particle, there are perhaps hundreds of elementary particles known. Too much of a mess. Now, strong interaction theory, which David helped pioneer, simplified that by reducing it to a smaller number of quarks and gluons. But still, even with our best understanding in traditional physics, there are dozens of different things that you can call elementary particles. The idea of string theory is to get all the different elementary particles, muons, neutrinos, electrons, up quarks, gluons, and so on, as different states of vibration of one basic string. So first of all, you can see that that's ambitious to try to interpret dozens of different elementary particles as all having a common origin. But secondly, to make it work actually requires the freedom from the extra dimensions, because it's the existence of extra dimensions that the string can vibrate in that makes it possible for all the different elementary particles we see to originate as vibrations of one basic string.
That's an advantage indeed of extra dimensions. But I'll again remind the audience that, in Einstein's theory of general relativity, and especially with quantum mechanics, the dynamics of space-time is a physical question. Space-time is dynamical, and the principles or the equations of our theory of dynamical space-time have every right to determine the number of dimensions and the topology and geometry of these dimensions as well. This is not something that is just given. Space-time is a physical object determined by certain criteria. And it's remarkable indeed that string theory does that in ways that allow it to, as Edward said, to describe, to unify all of the low energy particle manifestations of that structure. Eva, did you want to comment? Or you just have your hand up?
No, thank you. I'm happy to comment. I mean, as you were just getting at, in our best understanding of space-time physics from string theory and otherwise, space-time is emergent. It fluctuates, it's dynamical. Topology can change dynamically. And it turns out so can what you would call dimensionality. So it's a very interesting connected beast. This is related to what Ashok was stressing, that there isn't a tweak of the entire structure of string theory, but there are a lot of connected, there's a sort of connected picture of how different what we call backgrounds appear. And that includes dynamical and changing topology and even dynamical and changing dimensionality, as well as the dynamical and changing space-time geometry.
In that context, how should we regard space-time? One of the questions from Sneha Turbo Spares is space-time considered to be a quantum field or a quantum string? And how does space-time emerge, as Eva said? Who's going to take on? Juan, do you want to tell the audience how space-time emerges?
There are some examples that come from string theory where the fundamental description is in terms of particles that live on some dimensions, but the effective description is in terms of a space-time that contains gravity and contains extra spatial dimensions. So that makes people think that maybe in some fundamental description, space-time will not be present, and space-time will be something that comes out as an effective notion. It's similar to, for example, how if you put a bunch of molecules of water in a glass, they maybe condense near the bottom and form the surface of the water. And so that surface of the water was not there in the molecules, but came out of the interactions of these molecules. But it's a process we don't fully understand, and we continue to learn about this process, and subtle notions such as quantum entanglement play an important role. And perhaps one of the most interesting questions is whether time also can emerge in this way. So having some nice example where all of the dimensions of space-time are not present in the original description, and that we don't have yet.
Question about extra dimensions, just in the context of if there are predicted extra dimensions or possibly fluidity and dimensionality, how does that jive with our experience of the world as having 3 dimensions? Where are those dimensions? I think some of these questions from the audience are trying to get at this question of like, why don't we see them? Where are they? How could they be here?
Juan, did you want to reply?
Yeah, so I think so. If the basic idea is that the extra dimensions can be small, and so just as an example, let's say there is 1 extra dimension. So the extra dimension could be a tiny little circle. Now, if particles were classical balls, point-like balls, moving classically, they could move in the 3 spatial dimensions of space and also in the 5th dimension. So they would have an extra sort of degree of freedom. But in quantum mechanics, the momentum of this ball along the extra dimension is quantized and has some energy levels. And so thanks to quantum mechanics, the energy of those states where the particle has non-zero momentum or is moving in the extra dimensions has more energy. And so if we look at, has some quantized energy levels and have higher energy. So if we look at very low energies, we will only see the particle with a wave function which is completely smooth or completely translation invariant or constant in the extra dimension. And that particle will effectively behave as if it was moving purely in 4 dimensions. That's, I would say, well, that's how I can most simply explain the mechanism. So it's important, two things are important. One is that the dimensions are very small, and they're so small that quantum effects become important. And quantum mechanics then removes or effectively removes from the low energy description the particles that are moving strongly in the extra dimension.
Okay, Jerome.
Yeah, just to add a little extra amplification to what Juan was saying. Sometimes we use this a simple analogy of an extra dimension being rolled up like in a circle. So an analogy is you take, for example, a piece of hose pipe, and you imagine you're a little ant walking along that hose pipe. Then you can walk along the long, big linear dimension, but you also can walk around the small direction. So a small creature could probe this extra wrapped up dimension. But if you stand a long way away from this hose pipe, then you just see the line and you no longer see that extra dimension. So that's exactly the way in which we would conceive the way in which string theory would work. That there's a point in space, just where my fingers are, for example, and that would represent the 3 spatial dimensions that we are all aware of. And there's a time dimension. I could tell you what time I'm pointing to this point. But in addition, if we could zoom in, we would see all these extra dimensions. And that's true of every single point around us. So every single point around us would have actually these extra wrapped up dimensions. And we would need to zoom in to very, very small scales to see that extra structure.
Jim Gates. Raised your hand. Jim?
Sorry about that. I had some trouble getting unmuted. I just wanted to point out for our audience that there are variants of strings that more or less realize the idea that Eva talked about the fluidity of dimensions. And one particular set of examples were constructed by Henry Tye back from the mid to late 80s in what they called a free fermion approach to string theory. In these theories, the fundamental degrees of freedom are actually fermions, but space-time is emergent, as a number of our colleagues have commented upon. So there are lots of aspects of string theory that are little studied that will probably shed light on this question about the emergence of space-time.
Yeah, I just would like to end by confusing you all by saying that we're beginning to understand perhaps how space-time emerges, but it's mostly space. Although we combine space and time as Einstein taught us. What we really, I don't think, understand yet in a deep way is how time itself can be emergent. In any case, let me ask a question that was asked by Abyashi Maudlik, who asked about whether supersymmetry is a necessary ingredient for the formulation of string theory. And are you all bothered by the fact that there's so far no definitive experimental evidence for supersymmetry? And we have Eva, who will tell us that it's not necessary, I think.
Well, let me just say a couple of things to that. For the broad class of attempts to model realistic physics using string theory, with one exception, they all have supersymmetry at some level. But generically, I would say, and I think this is easily defensible, These are the scale at which supersymmetry would appear is indeed a very short scale, a very high energy scale, well beyond the reach of the colliders. It could work at quite a wide variety of scales, so we don't know. But the theory is perfectly consistent with indeed a high scale. The exception that I'll raise, which maybe David himself can comment on, is that if QCD proper is a string theory, it is completely non-supersymmetric. So that would be a different sense in which supersymmetry is not required in string theory. But there are lots of interesting indications that that supersymmetry might be relevant from sort of bottom-up arguments. But those have been constrained to some extent. And meanwhile, the theory itself has plenty and arguably many more backgrounds without so much role for that symmetry, even though it's kind of microscopically there. So it's just an interesting question, but it's not a constraint on the theory.
Jim Gates?
So the point I would like to make here is that for people who are not in the field, the story about low energy supersymmetry was universally accepted until the LHC turned on twice and didn't find it. But for many of us, the expectations were never really well grounded. And as I spoke in my popular talk yesterday, as early as 2006, I actually wrote in an article in Physical Today that I did not expect for low energy supersymmetry to emerge, although I am one of the strongest proponents for supersymmetry that I know about, longer than most people on this call. And so the idea that the LHC probing essentially what's known as the minimal supersymmetric standard model, and they're not even probing that, they're probing something called the constrained supersymmetric minimal model, leaves lots and lots of rooms in parameter space for supersymmetry to be out there for us to discover and beyond the reach of the LHC. Our colleague Nima Arkani Hamid has talked about split supersymmetry. So there are lots of ways to get around these expectations that were engendered in the public discussion.
Yeah, it's clearly too early to totally give up on low energy or observable in the next few decades supersymmetry. And partly in response to Eva, supersymmetry is, in some sense, inherently part of the string theory framework. Most non-supersymmetric versions or theories are often regarded as broken supersymmetric solutions.
Right. I'm just saying that it's at a very short scale. It
could be.
Yeah, I mean, it's in there. I was saying it's in there, except in your theory, which is QCD.
Here too, one of the hopes for understanding flux tubes, which look like fat strings in QCD, which was one of the experimental motivations that originally led trying to understand the strong interactions to string theory. One of the most likely hopes that I have is that there will be a useful string description, dual description of QCD, which is probably going to be gotten as a deformation of a dual description of a supersymmetric version of QCD. That's the most likely path, in my opinion. So supersymmetry, we didn't know about supersymmetry. I don't think much progress would have been made at all in string theory. It naturally contains it, and it's attractive for many other reasons, as you know.
And David, by dual description, you don't mean like an alternative. You mean dual in the technical sense, right? For our audience that doesn't know the technical meaning of the word dual, what do you mean by dual?
So in QCD is very simple when one looks at short distances, very high energies where you see roughly, asymptotically freely moving quarks and gluons. But at large distances, you see the proton, the neutron, the pi meson, and one phenomenological description of them, which is very successful, is as confined flux tubes of chromodynamic flux, which look like fat strings. And we have been searching, if you want, for decades for a alternate mathematical description of QCD in which the basic objects would be these fat strings. In supersymmetric cousins of QCD, that is indeed the case. And one could hope to, if we understand that dual description in the supersymmetric versions of QCD much better, we might be able to deform that description in ways which we kind of know how to do to the real world, to real QCD. So that's the hope. And it's a subject of much investigation nowadays. Okay. Let's see. There's a question about beauty in physics, which has been often commented upon, and the role of mathematics in beauty. So there's a question from Tommy Chin, who asks, as a theorist, how big a role does the beauty of nature play while getting inspiration for a new idea for a theory? And by the way, how do theorists guess a new theory at all? Does anyone want to explain how they get new theories, new ideas, and whether beauty plays a role? No beautiful answers?
Well, let me give you an unbeautiful answer. So I think the beautiful thing is that it works. So I think that this is the most important thing, is that there is a consistent framework. Now, beauty, well, is a bit in the eye of the beholder.
But we all recognize it, or we often recognize it. I kind of agree. Beauty, and I equate the first approximation with power. A physical idea, concept, framework is beautiful when it is short, concise, deep, but mostly it has power. Edward, would you like to comment?
Well, I think that the beauty of modern ideas in physics, or for that matter, mathematics, is very difficult to convey to someone who hasn't worked in those subjects. But if you do work in physics or math, the beauty of powerful ideas there is as apparent as the beauty of music. That you might take that as an analogy, because the beauty of music is likewise difficult to describe in words.
Mm-hmm. And innumeracy is similar to deafness. Nathan.
So I wanted to just repeat what Ashok said earlier. The fact that you can't tweak a theory, for me, is something beautiful. So for me, that's one aspect of how to see if a theory is beautiful or not. Hiroshi.
Yeah, so this is a part of the point about power. But one of the pleasure of working on this kind of field is that sometimes you encounter unintended applications. So you develop theory and you develop mathematics, and later you discover that what you knew had totally different applications. That was, for example, in the case of string theory, which was developed to understand strong forces, but turned out to be useful in understanding gravity. And there are many other instances like that. When I was a high school student, I read a book by Henri Poincaré, which said that one of the measures of science is whether that influences, how much it influences other areas of sciences. And I partly think that some of the beautiful mathematics and theoretical physics has to do with how powerful it is in that way. And string theory certainly has been like that.
Okay. So there's a question by Adia, who asks, can string theory explain something about the Big Bang cosmology? And there's another question which is connected to this, which is does the discovery and exploration of the nature of dark matter and dark energy have consequences for string theory? So, Eva.
Well, as in my one sentence reply to what is string theory, I'd say that's a big goal of the theory, and it's something that a number of us have worked on over the years and still do. So one very broad brush thing that goes in favor of this is that, you know, we talk about this untweakable but very complicated connected theory. And you know, most of it has positive potential energy, the kind of thing that drives the expansion of the universe. And there's a big ongoing theoretical campaign to understand how the dark energy, the accelerated expansion of the universe, manifests itself in string theory, and what kind of early universe dynamics emerges from that. And that's led to some models that are self-contained and even give some, in some cases, observational testing that we can do at the kind of model dependent level I mentioned earlier. There's still a huge amount to understand about this. So if we worked with the opposite sign of the cosmological constant, one of the big contributions in the field from Juan was to understand how to formulate that in what we call a complete quantum gravity sense. Those are very important and very interesting kind of backgrounds of this theory. But most of the theory is up at positive potential energy with an expanding universe and with more complex solutions to the equations of motion. And in that context, there are steps along the way, but there's not yet a complete framework to even formulate what it is we want to calculate, let alone how to calculate those quantities. So it's a very exciting challenge. And given this discovery of the accelerated expansion of the universe as part of the whole precision Big Bang cosmology, we can all think of ourselves as data-driven in trying to understand the physics of that observation in a fundamental way. So I hope that helps. There's a lot more to say about this, but I'll stop.
Amir?
Yeah, I think that's an extremely important question. It's actually the one that I think about a lot these days. So the actual mathematics of how particles come together when they get crushed at the Big Bang singularity is very much like how they get crushed at the center of a black hole. And if in black holes, we are finding all these new effects of string theory, where instead of everything reaching a point, because so many particles are involved, new effects happen and they swell up into these big fuzzballs or whatever. These effects seem to imply corresponding effects in cosmology, where instead of the black hole singularity, now we have the Big Bang singularity, and instead of the black hole horizon, we have the cosmological horizon. So you get some kind of rough predictions already from what we have learned about black holes for new kind of dynamics at the horizon scale for cosmology. Now, the ideas we have about that so far are very rough, but they're at the right scale. And interestingly, they are telling us things which could connect to, in fact, dark energy today, or in fact, the energy you required for inflation in the past and things like that. So I think that's really the new frontier we should be attacking in string theory with all our understanding of strings and black holes and all that we have learned, what's actually happening at the Big Bang, because there are a lot of particles are coming together exactly like in the black hole.
Pedro.
Yeah, let me just make one comment, which I think is also related to a previous question about observation of string theory and whether we could observe string theory. Let me just mention something for a general audience, which is that often these observations and these realizations of observing things that are related to string, that could be related to the theory of quantum gravity, come as a surprise. So maybe we are not expecting, and then there is an experiment that reveals something very deep about quantum gravity. So I remember a few years ago, there was a false alarm. We thought that we had received some gravitational signal that was some gravitational waves coming from the Big Bang, basically. And it was an exciting time. We thought, okay, this is a new quantum signal, a new signal we have to explain. I remember I was landing in Trieste. There was a string school, and Juan and Nemo were also lecturing at that school, and both were changing their lectures on the plane to talk about the Big Bang and inflation and so on. And then it turned out to be dust. But so sometimes it happens that we think that we are not expecting, and then there is a wonderful experiment. And indeed, the Big Bang is a great potential for getting a new signal, because things are very, very small. Quantum mechanics is very important. Gravity is very important. If somehow we receive some quantum gravity signal from the Big Bang, this would be spectacular. And it could be, because we thought already that it was happening once. So it definitely could happen.
Gabriela, did you want to add something?
Yeah, I wanted just to make one remark that the Big Bang in the modern view of cosmology is no longer to be regarded as in the old days as the beginning of time. The hot Big Bang of standard cosmology is the end of inflation. It's not the beginning of anything. Now, this being said, there is a question of what caused inflation, what was there before inflation, and those questions are really very interesting. And these are questions like the singularity in the black hole, to which maybe string theory has interesting thing to say, but forget about the Big Bang being the singularity. The Big Bang that we know something about is the reheating of the universe at the end of inflation. That's the hot Big Bang, nothing else, experimentally.
Well, that's the Big Bang we see.
Exactly. The other, we don't know much about. It's on speculation. It's only speculation.
Which we're deeply engaged in.
Yes, absolutely.
So go back and ask, some of the questions that have been asked are sort of more basic, but might be confusing for some of the audience. So one of them is Manel Oliva, who asks, why is string theory called string theory? So there are many parts of this question. Why is string theory called string theory? We don't call quantum field theory particle theory, or sometimes we do. Are particles like strings? Is there a better name for string theory? Quantum field theory describes particles, but the more basic description is in terms of quantum fields. There are attempts to describe string theory as well in terms of string fields. It's not as well developed, and the perturbative treatment, when the interactions are weak between strings, are well described by the analog of Feynman diagrams, in which elementary strings join and split to describe their interactions. So string theory is sort of analogous to particle theory, and quantum field theory is sort of analogous to the much less well-developed string field theory approach. Does anyone else want to address this? And Edward.
Well, I'd say that this is, again, a little hard to convey to a wide audience, but string theorists, in a sense, fundamentally don't really understand what the theory is. That's actually part of the fascination, that one has made so many remarkable discoveries while at bottom not really understanding the theory. So as a string theorist, my dream is that one day we'd understand the theory well enough that we'd know what it actually should be called. In the meantime, we do the best we can with what we've got.
Shiraz.
Just an observation about the name. I mean, the name, of course, there's some historical baggage to it, and that's why it's stuck. And it would be hard to change the name because as the field grows, we deal with so many different things that it's hard to find one word that encapsulates it all. And so I think we just stick with the historical name. But just about how appropriate that is, we could go to this conference and ask how many of the talks, how many of the 60 or 70 talks in the conference actually deal with strings in a detailed way, in the way would justify that name. And I would think not more than 4 or 5 of the talks in the conference would do that. So, I mean, it's not a very good description of what we actually do, I think, anymore. But it would be too difficult to find a replacement. So I think we just stick with it.
So there's a question from some of our audience who are obviously very interested in string theory, but don't know very much. And they ask questions about how can they learn more about string theory. So Avisha asks, how does a high schooler like me get into string theory? Who would like to give advice to high schoolers who would like to get into string theory? Jim.
So this is a question I get quite often because I have a fairly broad and consistent and constant interaction with high school students, undergraduates, what have you. And the answer I always give them is learn as much physics and mathematics as you can. As emphasized earlier, string theory is not a constant target. And so what you need to do is prepare yourself as deeply and as well as you can to deal with string theory should you continue along the line and be in the position to engage it. So study, study, study. Math, math, physics, physics. That's my answer.
Right.
There's a follow-up question in the chat asking, is there an equivalent good book in string theory like Z's book for QFT? This is a chance for people to promote their own books.
Well, there are a bunch of good books. They usually require quite a bit of preparation. It's not easy to start with string theory. You definitely need to know something about quantum mechanics. You need to know something about quantum field theory. Those are sort of prerequisites at some level. I don't think there's a great book yet. Some people in this audience to write it. I don't think we understand the theory well enough to be able to explain it in very simple terms without. But there are excellent books out there. I don't think we should go through the list. Igor, did you want to?
Yeah, I was just going to mention Barton Zwiebach's introductory book. I think it's very pedagogical, and for those with a basic undergraduate curriculum, it seems to provide a good entryway. I'm not sure it's an equivalent to Z's String Theory in a Nutshell book, but seems like a good pedagogical book. And it also begins with subjects that are more basic than string theory too.
Could you repeat the name of the author again for that book?
Barton Zwiebach. Another question was from Stefano Gaivota. What level of mathematical technique is required for a student to begin studying string theory? And if you don't have the mathematics, are there any more intuitive descriptions to help getting a foothold in this direction? Any more advice? Let's see, who has their hand up? Samir, you wanted to? You just have your hand up. Samir, Eva.
I just wanted to suggest for the high school kids to learn special relativity. And regarding mathematics, it's a beautiful thing because it doesn't require anything beyond what you would learn in a beginning algebra class. So if you read about that and you get hooked, that's probably a good starting point. In general, I think getting as Jim said, getting a broad physics education is really the best bet, both because you learn appropriate methodology, but also because you learn how the world works. You'll get exposed to other areas, which are also exciting, and you can make a more informed decision about what to pursue. But for the high school kids, even reading Einstein's original popular book on the subject will give you a step-by-step guide to special relativity, one of the great breakthroughs in physics.
So, okay, some advice. There are a few provocative questions here, which we might ask towards the end, like, what would make you give up on string theory? Igor, did you? Igor Klebanov?
Sorry, this was a leftover from my previous comment.
Well, what would make you give up on string theory?
That's a very good question. Well, I think it's such a broad framework, and I've been working on it one way or another my entire life. So I can't see myself giving up directly on it, but if there is something incredibly exciting in a more, say, a discovery of something new in another field, I can imagine taking a little time off. But I think string theory is very much tied to what we know about quantum field theory and these so-called large N limits. And this is very dear to my heart. So one way or another, I'll keep working on it, I think.
Ashok.
I think I will give up string theory if we find a mathematical inconsistency. I mean, my main inspiration for working in string theory is the mathematical consistency of the theory. And if that is found to be at fault, I'll certainly give up.
So do you know of an historical analog where a theory as rich as string theory was given up because of mathematical inconsistency?
Yeah, I don't know. I don't think there was a historical analog of string theory that which are so mathematically consistent and yet turned out to be wrong.
Okay, Nathan.
May I add, David, may I add something? I mean, I gave up on the old string theory when I was young, and this was because there was a better theory that came out. So one day that people will come up with a better theory of quantum gravity, also explaining the standard model and all these parameters, then I would give up.
Well, in the question period, people, David, no last name, has asked, what about loop quantum gravity? Is that a viable alternative to string theory? Does anyone want to take on that? Is loop quantum gravity a viable alternative to string theory? Edward.
I'd say no, honestly. It's just a restatement of some of the questions in a not terribly informative fashion.
Any defenders of loop quantum gravity?
Well, no, I would only add to what Ed was saying. I mean, it looks to me that loop quantum gravity is a technique to quantize gravity, which doesn't modify the basic theory. And it looks to me, I have this analogy. There was a theory of the weak interactions due to Fermi, and people tried very hard to quantize it, but failed. And what we really had to do was to modify deeply the theory to make it softer and so on and so forth. And I think somehow this is what I reproach to loop quantum gravity, that it is not radical enough. I mean, it's a technique and not a modification.
Yeah, I mean, it's more, Einstein's theory is more equivalent to Fermi theory of the weak interactions.
Exactly.
Effective low energy theory. Loop quantum gravity is an unsuccessful attempt to.
My opinion.
There are no defenders of loop quantum
Because
gravity.
this is the wrong community to ask the question.
Okay.
Nathan, may I weigh in here, because I think among all of us on this Zoom, I probably have the broadest interaction with members of the public who are not committed to the ethos of this group. And it may sound to our audience as if we're all in a religious cult, but we're not. Some of us, like Gabriel mentioned, he looked at it. I know I've looked at loop quantum gravity in a serious way, trying to figure out, is it a true alternative? And I would tell anyone, no, it is not a true alternative to string theory. String theory, as many people have said, for many of us who have looked seriously at the question, is the only game in town right now.
Right. So we're nearing the end of this marvelous session. Nathan, when are we cut off momentarily?
No, the idea is, to go until 3:30. Of course, we can go a little bit, well, for another 3 or 4 minutes.
Right.
But we can go a little over time. That's up to you.
So I'm going to end with anybody can contribute. There's a question from the audience. Well, I don't forget. Hard for me to find out who asked it, but it was, what are you most excited about in string theory nowadays? And I invite everyone to contribute until the session ends and the plug is pulled. So who is excited and would like to express what they're excited about in one sentence or two? And come on, you're all excited about something, I know that.
David, my hand is up.
You just spoke, Jim. People who I know are excited about things who haven't said a word. Well, nobody's excited. So, okay. So previous speakers. Samir.
I think I'm most excited about what we could be learning about the Big Bang, as we were discussing a little while ago. I was actually just playing with some very rough ideas of what black holes could tell us about cosmology, and I found something which I was confused about. And what I was finding was that when the expansion rate of the universe changed from the dust form, from the radiation form to the dust form, the black hole theory seemed to predict there would be extra energy. And I was thinking, surely that can't be right. We would have seen it in observations. And just about a couple of weeks later, I read papers saying there's a mismatch in the values of Hubble constants. If we just had some extra energy right at that time, it would fix something. Now, this could be totally wrong. It may be nothing to do with anything. But the fact that this automatically came up first from what I was guessing from black hole physics, and I actually found out about it later. I should have known about it. It was known to pretty much everybody, but I didn't know much about this mismatch of Hubble constants and that extra energy at that time would fix it. But I think it's very exciting that there is a new picture of the gravitational vacuum that's coming out of our understanding of black holes. And that picture really affects cosmology at the horizon scale. And I think people should take a look at it and be able to see whether it's right or wrong.
Okay.
It's working in either case.
Great. So fuzz geometries. Veronica, we haven't heard from at all.
Yeah, I'm very excited about the interconnectivity in our description of physics, of nature. Black holes are wonderful examples of that interconnectivity in the sense that they tie together completely disparate fields ranging from, not just string theory, but fluid dynamics, condensed matter physics, even quantum information. And I think this is not just a fortuitous fact, but something that really could then lead to much further progress in our understanding of physics.
Mukund, identify yourself so you haven't spoken.
Yeah, I'm Mukund Rangamani, an Indian physicist working in Davis, California. I'd like to echo what Veronica just said, but more generally, I think we live in an exciting time for science, and in particular for theoretical physics, which I expansively view as all of string theory being. And we see a lot of interconnectivity, and we've seen incredible progress in the last 5 decades, connecting disparate areas of what a priori would have been different subfields of physics, which have come together within the string theory ages into a beautiful framework. And this, to me, suggests that we are barely scratching the tip of the surface in terms of what the rules of nature ought to be.
Great. Serge Dubovsky.
Hi, my name is Sergei Dubovsky. I'm from New York. So I would give an answer maybe even more broad than what just said. I'm just feeling that every day I am learning something new. And I don't think there are that many areas of human activity which allow one to do that. So.
Okay, so you're mostly excited about learning new things, and there are plenty of new things to learn. And
yes.
No one else is excited about anything? In which case, we seem to. Shiraz is always excited. Shiraz.
I'm excited about all the various hints that we're getting, that general low energy constraints together with completions at high energies are more constraining than we thought about various theories. And the possibility that classical theories of gravity that have a classical limit could be completely determined by low energy constraints and lead you to inescapably to the statement that string theory is the only such completion of Einstein gravity.
Okay, I think we've run out of time, and I would like to thank all the speakers for undertaking this very difficult task. And hopefully it was enjoyable to us as well as to our audience. And let me just turn for a final remarks to Nathan Berkovitz, who is the director of ICTP-SAIFR, who's put all this together. Nathan, would you like to close the session?
So thanks very much. So let me start by thanking, of course, Ana Luisa and Malena and Jandira, who work very hard in all our activities, and also Bruno Oliveira. So he's doing the translation into Portuguese, and he's done an excellent job for the translation yesterday and today. And then, of course, I'd like to thank David and the 4 panelists for all their hard work. This was actually our 3rd meeting. We already had 2 rehearsals. So I think it went very well. And of course, all the panelists. So we'll see all of you tomorrow for the next week of the Strings meeting. So thanks everybody for participating, and we'll see a lot of you tomorrow. So, bye-bye.